first point eigenclass. That class is denoted by 1/2 of the point eigenclass, so it's a kind of torsion effect, and that class vanishes. So that's a string manifold. Like a spin manifold is one where the Stiefel-Whitney classes vanish. String manifold is one where this additional characteristic class vanishes. And so this is a class in degree 4. So this is a vanishing in degree 4 cohomology of the manifold. And then I will explain in a second why it will be necessary not just to talk about if the class is 0 or not, but also to have a way of saying how the class is 0, how it vanishes. Like if you have a spin manifold and the second Stiefel-Whitney class vanishes, that's fine, but not enough to let the electron move in the manifold. You need a spin structure, a structure that parameterizes how the class vanishes, and usually there are different choices of structure, and it's important to select one. So here the question is, what is a string structure on the manifold? And we want some geometric way of talking about the vanishing of a degree 4 class. And that's a non-classical theory, because if it were a 2 class, for example, H2, then you know that this group is geometrically realized by line bundles on the manifold, right? So there's H2 of the manifold. That's isoclasses of U1 bundles on M up to isomorphism. And then I just need a bundle that represents my class. And then I would say, choose a trivialization of the bundle, then the class is 0. But here we have a 4 class, and it's not it's not part of classical differential geometry what a geometric structure is that parameterizes 4 classes. But in higher differential geometry, there is something in particular, or even more general, there is a way of generalizing arbitrary classes in K plus 2, plus 2 is therefore, because here I put K bundle gerbs with U1 structure group up to isomorphism. So this method of talking about bundle gerbs is a method to realize cohomology classes in arbitrary degrees by geometric structure. And if K is 0, then we get back the U1 bundles. Okay. So just, I don't want to introduce the things in detail, but just to remind you, like a bundle gerb is a structure that looks like, so here's over M, of course. So you choose some kind of cover of M, some resolution, can be an open cover, can be a fibration, can be anything. And then on the double fiber product, have a line bundle or U1 bundle. And then there is coherence data on the higher intersections, which I, for the purpose of this talk, I just don't mention. And so you see that there is, for a K-gerb, there is this recursive definition that you put this and then a K minus 1 gerb here. And then that's how it works. This theory is made of. All right. Let me mention that there is also even more differential geometry by putting connections on these things. So I use a nabla symbol to indicate that there are connections, and that realizes differential cohomology. So that's just a note if you've heard about that. So there is an extension of ordinary cohomology theories by differential data in some sort of conceptual clear way, and there are connections on these gerbs realize that extension. All right, so now, yeah, so degree 4, so that's 2 gerbs over M. And indeed, there is a specific 2 gerb over M whose characteristic class under this isomorphism is the 1/2 Pontryagin class. There is an object here. It's called the Chern-Simons 2 gerb of M. It's constructed by Michael Murray, Alan Carey, and other Australian fellows 20 years ago. And that is called Chern-Simons 2 gerb because in general, Chern-Simons theory theory has a 4 class, like a general 4 class. And then a 2 gerb has like a holonomy around 3 manifolds if it has a connection. So it also has a connection here. Yeah, never mind. And that connection on a 2 gerb has holonomy along 3-dimensional manifolds, and the holonomy of that Chern-Simons 2 gerb is the classical action functional of Chern-Simons theory. That's why it has this name. It's not that relevant here. Here it's just relevant. There is a specific gerb, it has this specific class, and now because these gerbs form a category or even higher category, we can talk about trivializations of that 2 gerb, like isomorphisms to the trivial 2 gerb, and that's going to be our notion of string structures. So, string structure will be, by definition, a trivialization of the Chern-Simons 2 gerb on M. That's our working definition of string structures. So later I will provide an alternative definition, an equivalent one, namely by principal 2 bundles for the string 2 group. It's going to come later. So right now I want to explain why these string structures are necessary for supersymmetric strings, for the supersymmetric sigma model. I just want to outline the argument, how all this came. So why is this class interesting, right? Why is it interesting? So there is a general procedure called transgression that involves these loop spaces. So in general, transgression map, when I write gerbs, I just mean 1 gerbs. So if I have 1 gerbs over a manifold X, then transgression takes that to U1 bundles over the loop space of X. I'm putting connections here because I want to insist that this is a functor. To have a functor, one needs to include the connections. On the level of isomorphism classes, the connection is just auxiliary and goes away. But if I want functors, I need the connections to have that transgression thing. So that's something that was started by Brzezinski in the 90s. And also physicists like Gabetsky used it like a lot. So what's the point here? For example, in Wess-Zumino-Witten models, when X is a Lie group G, then gerbs with connections on G, they model the B fields. So B fields. This is true for general X. I mean, gerbs with connections are the B fields for sigma models. In particular, when X is a Lie group, then we are the Wess-Zumino-Witten models that they have been studied a lot. And then the B field transgresses to a line bundle on the loop space, which is a very famous object in conformal field theory. So, okay, so how do we get the Chern-Simons 2 gerb involved here? Well, there is another vertex here, so I can put 2 gerbs on M, and now apply the old transgression to the loop space of M. And then here we have double loop space of M, loops in loops, which is just the same as maps from the 2 torus to M. Okay. And then this transgression business also holds like this. So you see the pattern is transgression takes a K gerb on a manifold to a K minus 1 gerbs on the loop space. So it takes a 2 gerb on M to a 1 gerb on the loop space.
That's a good question for the previous example. The object when you go there, is it to do with the Kac-Moody, like the infinitesimal version, something to do with the Kac-Moody algebra? It looks like a central extension of.
Yes, it has something to do with that, exactly. So what you get when you take a gerb over G and transgress it, you get a line bundle over LG. And sometimes you have even more things. For example, the gerb can be multiplicative, compatible with the group structure. then the transgressed line bundle will also be compatible with the group structure, which means that it is a central extension. So that line bundle will be a central extension of the loop group. And if you pick the correct gerb, then you get the basic or the universal central extension of the loop group, whose Lie algebra is the Kac-Moody algebra. Yeah. All right. So transgression has also this arrow here, like by general nonsense, and so by opposition, we got this diagram. And so this structure fits here into the following way. So here is this Schoen-Simons 2 gerb. Does have a connection, by the way, so it's useful. And so, or maybe let me first like comment on the homological point of view. So what are the classifying cohomologies in this diagram? So I told you that this is H4 of M. So this here is H3 of the loop space, geometrically realized. And this here is H2, because it's line bundles or U1 bundles of the double loop space. So of this mapping space, right? C infinity M. Okay. And here is this 1/2 Pontryagin class. Okay. And then been asked, where does it go under this map? Okay. And it goes to the Chern class of a specific line bundle on the mapping space of the torus, namely a line bundle that appears in the sigma model theory, namely this Pfaffian line bundle. So here is this Pfaffian line bundle on this mapping space. And so the Chern class is the transgression of this 1/2 first Pontryagin class. So this is a result by Fried in the 80s, I think, one of the first results of Fried. And that is the point why string manifolds are important for supersymmetric sigma models, because this class transgresses to the Chern class of this Pfaffian line bundle. And I don't have much time to talk about this, but this line bundle represents the anomaly for the quantization of the fermionic part of the sigma model. So there is this theory, you take the worldsheet fermion has an action functional involving the Dirac operator on a surface. Here it's a torus on the surface. But it's twisted by the pullback of the tangent bundle, so it depends on this map from surface to manifold on the worldsheet embedding. So varying this map, you have like these Dirac operators, and associated to that family of Dirac operators, there is this Pfaffian line bundle, and the fermionic action functional, which is supposed to be a function to be integrated, is unfortunately just a section in this line bundle. It's this Berezinian integral, which gives a section in this Pfaffian. And in order to make it a function, it is essential to trivialize this theory of anomalies, or in this sector of the physics, that's called an anomaly, right? It's a function, if you have a function, but it's not a function, it's a sectional line bundle, but you want a function. So what you have to do is to trivialize the line bundle, and that means the Chern class of the line bundle must be trivial. And here, it is trivial if this class is 0 because it transgresses to the Chern class. Okay, that's why we're interested in string manifolds. And that's why we're interested in string structures, and why it's important to realize these things on a categorical level by geometric objects. Because I told you that the Schoen-Simons 2 gerb, which is an object here, now suppose we have a string structure, a trivialization. It's a morphism in this category, an isomorphism, and we need the functoriality so that it transgresses to an isomorphism between the Pfaffian line bundle and the trivial line. So only if we have a specific isomorphism, we can translate the section into a function, because otherwise we just know there is an isomorphism. It doesn't help. So we need a string structure to get the trivialization of this Pfaffian line. And the transgression of these gerb stuff, that tells you exactly how it's done. Actually, there was a necessary refinement of this theorem of Fried. Fried just proves that on the level of cohomology this works. And there is a newer result, a very newer result by Ulrich Bunke, 2010, who actually proves that the transgression of the Chern-Simons 2-gerb is canonically isomorphic to the Pfaffian line bundle. Okay, so that's a very important result. It's kind of underestimated, but that's the actual point where it's proved that string structures are really relevant or help to cancel the anomaly of the superstring. All right. So 2 further comments. The one comment is, so here we made this detour over the loop space. So we arrived at the double loop space. This transgression, this arrow here, only this works for any surface, any closed surface. So I can replace the torus by any closed surface. And all the results are true for any surface. So a string structure not only cancels the anomaly for tori, but for all closed-oriented surfaces. Okay, that's very nice. So one choice, one string structures cancels all the anomalies for all surfaces, right? In the string perturbation approach, you have to sum over all the surfaces. That doesn't matter. It's done for all surfaces. So what's about this part of here it's kind of saying, well, there is a gerb on the loop space. So what is that gerb on the loop space? That's the lifting gerb on the spin lifting gerb on the loop space. And what that exactly means, I'm going to explain next. Are there any questions at this point? Right, so I want to give some general explanation of lifting theory, which we then apply to the loop space, for example. So very general, so here's some general knowledge stuff. If you have a central extension of Lie groups, this central extension of Lie groups, and you have a G bundle over some manifold, P G bundle over some manifold, X. Then there is the question, does the structure group of the G bundle lift to the bigger group G hat? That's a non-trivial question. It can lift and it cannot lift. And if it lifts, there can be different choices of how to choose lift. So lift means we have a G hat principal bundle P hat such that if you push along the structure group, you get the given bundle P. That means a lift. All right. And associated to such a lift, there is a lifting gerb. P over X. And that lifting gerb has a property that the trivializations of it, that means the isomorphisms to the trivial gerb, that's a category because one gerbs for the 2 category. This category is equivalent to the lifts. The G hat lifts of P. Aha. So how does this come about? So there are several things I could explain. If you look at this from the picture of transition functions, and this has G-value transition functions. If you try to lift the G-value transition functions to G-hat-valued transition functions, you can sort of do that, but the lifts won't satisfy the co-cycle condition. But by a snake lemma argument, the co-cycle, the error is A-valued then. And to get an A-valued Čech co-cycle in 1 degree higher. And that's why you come from bundles to gerbs, basically.
Is a coefficient gerb.
Yeah, the lifting gerb has coefficients in the group A now, exactly. Yeah, so in the example we're looking at, A will be U1 in a moment again. Yeah. There are other applications, for example, I could put the spin group here, spin goes to SO, then the kernel is Z2, then I get a discrete gerb with a discrete structure group. So there is a lifting gerb associated to the problem of lifting the structure group, say of a frame bundle to spin, and then the trivializations of that gerb are the spin structures, the lifts. Okay, so gerbs are very useful to model categories of let's say things that solve obstructions. Okay. There's also a version with connections. I just want to mention that. So let's put connections here. So one can first put a connection on that lifting gerb and then consider connection preserving trivialization that lifts with connections. That's all easy. And the application of that over here would be here. So we have the Chern-Simons 2 gerb, which lifts here. And there is also this transgression here. And here it lifts to a lifting gerb. Let's just call that gerb LM. So that's a gerb. I'm claiming it is a lifting gerb. That's in fact something one has to prove. So LM is the lifting gerb for the following lifting problem. Namely, the central extension is exactly like this universal central extension for the spin group. And the bundle is the looped frame bundle of the manifold M. So you take this, okay, let's say spin M denotes the spin-oriented frame bundle, right? M was a spin manifold. So this means that the frame bundle is a spin bundle. So this is a spin bundle, M. And we just take loops everywhere, free loops everywhere. And this is an L-spin bundle, and you'll see now it makes sense. So this is the lifting gerb that obstructs lifting the structure group of this bundle to this bigger structure. And that's what also appeared in the string theory literature in work of Killingback, also Witten, as like a pre-version of what a string structure also could be. A string structure could also be a lift of the structure group of this bundle to L-spin head. Such a lift is a trivialization of this lifting gerb. And the lifting gerb is a transgression of the Chern-Simons 2 gerb. So by all functorality, if I have a string structure in our sense here, a trivialization here, because transgression is a functor, it transgresses to a trivialization of that lifting gerb. And by the theorem that says it's one of these lifts to L spin tilde, which Killingback called a loop spin structure. So a loop spin structure can be like extracted from our string structures, but in general, string structures are have more structure, more information, which we see by the fact that this diagram only accounts for anomaly cancellation on the torus. But once I've transgressed to the loop space, there is no way to get back to an arbitrary surface, just to surfaces which are loops of something. That's just the torus. All right, so there is a similar story for two-group extensions. So I don't want to go too much into the detail. Maybe let's start with the point. The point is that there is this categorical group extension, the string group. So the string group extends the ordinary group spin by the group BU1, two-group BU1. That's a two-group extension. And the lifting theory works like very similarly. So you have given an ordinary bundle for the spin group and asking, does the structure group extend to this two group? I will explain in a second a little bit more about two groups, just to make the point here that there is a lifting, well, two gerb now, because we are like one category way up. So there's lifting two gerb. Yeah, and guess what that two gerb might be?
Simon's 2 gerb.
Yeah, it's the Chern-Simons 2 gerb. Very, very good. The Chern-Simons, so it's another, so this is like a theorem that proving that a given gerb is the lifting gerb of a lifting problem. There is another theorem showing this. The Chern-Simons 2 gerb is the lifting gerb of this higher categorical lifting problem, meaning by this theorem that straightforwardly generalizes to the 2 case that the trivializations of the Schoenheim's 2 gerbe correspond to the lifts. And this gives the alternative formulation of string structures. The trivializations of the Schoenheim's 2 gerbes correspond to principal 2 bundles for the string group, string n, that lift. Yeah, I didn't mention that. Just so the bundle is again the spin frame. That's our P. That lift spin n. So by this equivalence, that's really now an equivalent formulation, right? So the other formulations of string structures, for example, loop spin structures, are not equivalent, just derived, but forgetting information. But this is really an equivalence. All right, I should say something about the necessity of the connections that are sometimes I drop them, sometimes at the game. So here I pointed out that transgression needs connections to be functorial, and we need functoriality because we want to transgress morphisms, the trivializations. And actually, because we're interested in this trivialization of this Pfaffian bundle, one can show that the choice of the connection is actually on the trivialization, on the string structure, it's actually relevant. Right? So there is this, I should write it, notion of a geometric string structure. Geometric string structure means trivialization of sentence, connection preserving trivialization. Preserving trivialization. So it's important that one, with this higher categorical context, it's actually additional information. It's not a condition, it's additional structure, the connection on the trivialization. And it influences the trivialization of this Pfaffian bundle. So choosing different geometric string structures, even if the topological string structure is the same, gives different anomaly cancellation. So it's really important to keep track of this connection. And that's why we are interested in this lifting theorem in the setting with connections, right? So we want to know trivializations of the Schoenheim's 2 gerbe. These connections are the sort of string lifts with connections of the spin frame bundle. And that was sort of difficult for a long time. It was solved 2 years ago by Mario's student, Roberto Tellez, whose PhD thesis was mentioned already 3 times in this conference. It was really great work, who figured out how to obtain this equivalence. And the answer was that one has to use this theory of adjustments that was invented by Christian for connections on higher categorical bundles. And so there is like, here I should like adjusted connections. So there is this sort of complicated or like specification one has to do in order to achieve this equivalence. And that means that geometric string structures are now equivalent to principal 2 bundles for string n with adjusted connection that lift this and the Levi-Civita connection here. Blah, 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 drop that. All right. Any questions? I'm trying to explain some general abstract theory and then like here the lifting thing that can be useful in very many situations. So another thing that might be useful is like if I explain what a 2 group is actually. 2 group. Fine to think about them as cross modules, which means that one has two Lie groups. So I would call H and G. There is a group homomorphism T, and there is an action of G on H by group automorphisms. Structure of the cross module can be summarized in that way, and then there are some conditions how that action is compatible with T. That's the structure of a cross module. And associated to such a cross module is a 4-term exact sequence. One can just kind of characteristic for the cross module. One can look at this group homomorphisms, and then extended by kernel and co-kernel. Kernel, by these axioms that are imposed, is always an abelian group that can be seen as the fundamental group of the two group I1 of G, and the co-kernel. Yeah, so now with Lie groups, it's a little bit complicated. There are some conditions one has to pose so that the quotient of G by the image of H is again a Lie group, but usually it's satisfied that plays the role of pi 0 of the two groups. Two groups are topologically two types, so they only have two, pi 0 and pi 1. And like, okay, that's all right. And maybe I can also explain what one of these principal two bundles is in that setting. So here, these lifts. So we start with an ordinary bundle for spin, but want to lift it to the two group string n. So the lifted thing will not be an ordinary bundle, will be principal two bundle. And it will look like one of these bundle chirps here, because we have, due to Vanius' work long ago already, we can present principal two bundles by non-abelian bundle chirps. So that's how does such a non-abelian bundle chirp look like? I just call it two bundle for such a two group gamma. And the picture is like almost the same. So we have the manifold, we have a covering space of the manifold. On the double fiber product, that's always where the important information lives, where the information lives what the gluing data of such a thing is, right? For line bundles, it's a U1 valued function. For bundle chirps, the gluing data is line bundles. And for non-abelian bundle chirps, the gluing data are principal H bundles. So these are principal H bundles with an addendum, namely with a so-called anchor map to G pi. So again, there are like conditions one has to look at. The point is that one of the coherence data on the higher things that I swallowed will consist of taking tensor products of such things. Now, the category of H bundles for non-abelian H is not monoidal, so it doesn't have a tensor product. So one has to do something to make it monoidal. And one way of doing it is to impose this anchor map G with conditions, and that will furnish that was misleading. So of course H acts from the right on my principal bundles, but this anchor map will furnish a second H action from the left, commuting with the right H action. So it sets like the principal H bundle into a bi-bundle for H. And for bi-bundles, as you know, one can take tensor products, one can compose them over H. So, and this is where the cross-module structure comes in. So this is a two bundle for a two group. Looks like this. So by the way, if you the condition that the thing lifts means that I can like project down to spin and then get the given bundle. And here this means that we extend the anchor by this projection map here, call it P, say, to F. Then by the stuff here, this factors. And so we will provide an F-valued transition function, an ordinary transition function with values in F. And in case of string, this is gamma, this is F, and this is B1. So it's of VA. So here you have an F-valued transition function, which is the underlying spin bundle. Okay, so far the structures involved here. So the next thing I would like to explain is a bit what the string group is.
Yeah, so here, what example should I have in mind for G and H?
Yeah, I will now define the string group.
Okay.
That will be an example. Admittedly, it's a difficult example, a very complicated one. If you want easier examples of cross modules. So okay, so the easiest example is probably you take an abelian group and send it to the trivial group. Then the action is also trivial. That's a cross module of BA to this thing for A equals U1. So that's an easy thing. Then there's like the opposite. You can take an arbitrary group, map a point to the arbitrary group. That's how ordinary groups sort of sit in two groups. That's possible. Okay, these are of course trivial examples. Then there are extensions of this kind, BAF extensions. There's a classifying theory also. And there are also independent examples, for example, T-duality. There is a cross module where H is kind of looks like this. So I mean the groups can be really different depending on the application we are doing, right? So these are the groups in the T-duality 2 group. So here the map is just forgetting the U1 and inserting integers into reals of 2n. And so the string group I'm going to explain now. And what else? For example, if you have an algebra, let me explain this. So an algebra, say an associative algebra over a field, then there is a 2 group, I denote by capital letter out A, the automorphism 2 group of that algebra. The cross module is take the units of A and send them as inner automorphisms to the automorphisms of the algebra, and the automorphisms of the algebra act sort of or restrict to automorphisms of the units by obviously. So that's a cross module. Check the axioms. So to every algebra an associated cross module that's going to be relevant. Second. Okay. All right. Now the string 2 group. String. String 2 group. So the first construction of the string 2 group was given by John Baez, Urs Schreiber, and other people. That sort of looked very complicated. So later, Matthias Ludewig and I found a drastic simplification of that construction. And in fact, one can do the following. So it's a very general thing. I start with an abelian Lie group A, some Lie group F. So sort of I prescribe the kernel and co-kernel, kernel and the co-kernel. And so F has to be simply connected for the construction. But I'm going to apply that to spin, so then that works. This is U1. And the only further information I need now, this is now Lie algebraic data. So it's a symmetric bilinear form on the Lie algebra of F with values in the Lie algebra of A. It's a pity that Urs isn't there. I wanted to show him how to draw Maßfrag appropriately. Okay. And of course, this is like in Schoenwell theory, take at-invariant symmetric bilinear forms. F with values in A. That's the input data. And from that input data, one can construct a 2 group, and the string group is going to be a particular example of that. So for people who know 2 groups, they might be surprised that we take this input data, because usually you would take a class with 3 Lie algebra cohomology FA, because that's what classifies crossed modules. So crossed modules are classified by the group F, so pi 0, the group A, pi 1, and an action of pi 0 and pi 1, that's always trivial, and a degree 3 cohomology class here with values here, like homotopy 2 types are classified, right? And so you would expect that I insert a class like this, but now we know already that we're going to need these adjustments, okay? And Matthias, Ludovic, and I, we proved that a cross module will only admit an adjustment if its classifying 3 class is in the image of the Chern-Weil homomorphism, which goes from there to there. The Chern-Weil homomorphism is really easy. It takes a symmetric invariant bilinear form and sends it to this thing, to this 3 form. So using the Lie bracket and the given form. So for people who know what the string group is, they would expect exactly this, where this is just a killing form on spin or something. And that is obviously in the image of the Chern-Weil homomorphism, which tells us, using that theorem of Matthias and me, that the string group will admit an adjustment. Okay, fine. And the construction of such adjustment also goes by choosing a pre-image and doing stuff. All right, so yeah. So I was planning to explain exactly how this two-group pyramid will do it. So how are we using this B? The B, using the B, we define a cocycle, complicated notation, eta B tilde on the loop Lie algebra, cocycle. That's by basically taking, so this means loops in the Lie algebra. So I have a loop, okay, let's say F, G, 2 loops in the Lie algebra. So now it gets a little bit concrete, sorry. And send this to like basically the integral. So let's say the loops are parameterized from 1 to 0, from 0 to 1, doesn't matter. So I integrate over the loops and integrate B and then F prime of T GT. Okay, it's not a very simple. If you know about loop groups and have read Presley-Siegel, then this is what it classifies central extensions of loop groups. And indeed, so this is a Lie algebra 2 cocycle, and we show that there is, that classifies a central extension of Lie algebras by usual classification theory. And we prove that this Lie algebra extension integrates to a Lie group extension. So there exists a unique central extension. U1 goes to LF tilde. So LF tilde is the central extension of the Lie group of that Lie algebra, LF. Such that the Lie algebra extension is classified by that cocycle. Okay. So I need that extension for saying what the other groups in the crossed module of the string 2 groups are. So the group G, right? So I need here. Okay. So we want to define this cross module. So we don't want to define H goes to G, goes to automorphisms of H. So I start with defining G. G is the paths starting at the identity in the group F. Okay, do that. And H will be this central extension that we got from this cocycle. So this map that I need will sort of project to the base and include loops into paths. Yeah, maybe I have to can always restrict central extensions to subgroups or to the base loop groups. Okay, and then that's sort of clear. That's also the same in this construction of Bayes and his colleagues. But what was difficult there was to realize this action, and that was just that there is the problem. Okay, don't have too much time to get into the details. So the point is, so we define it as follows. So take a path and then do the following strange thing. Double it. I denote this by this symbol. So this means we consider a loop that goes along gamma and then goes back along itself, right? So it's like a flat loop. Denote this by this. So this is an element in LF then. And this element in LF acts by conjugation. So this is an element in L that I've parameterized from 0 to 2 because I doubled it in F. This acts by conjugation on the central extension. Also, just here. Right, it acts by conjugation because it's a central extension. So I choose a lift, then conjugate with the lift, but the choice doesn't matter because the choices are parameterized by things in the kernel. So that conjugation is well defined. And then we just have to show that this action satisfies the axioms of the cross module. That's in fact difficult. Here's this so-called Pfeiffer identity has to be shown. And we deduce that from a property of that central extension that we prove and discuss also a lot in our paper. It's called disjoint commutative. That's a property that has been kind of commutative, overseen in the discussion of loop groups so far, but many loop group extensions have that property. It means if you have two elements in the central extension projecting to loops with disjoint support, so that loops are sort of trivial, but only non-trivial on disjoint parts, then the two elements commute in the fibers. That's a property called disjoint commutative. We prove that this central extension has a property basically because the classifying cocycle here, this integral has this property, right? If f and g are only non-zero and for different t, then this will always deliver 0 in all cases. And that sort of shows that there's some triviality in the central extension. So that's a disjoint commutative. We just realized that it can be used to show the Pfeiffer identity here. But that was maybe a missing part that was listed by John Bias. So with that, the action is like, that's all. There's nothing more to say about that. No need to say more about this. That's the action. That's a full description of the string. All right. There's also a way of writing down the adjustment on that, but since I didn't really define what adjustments are, it makes sense to write it down, but there is a canonical way of writing down it. All right, so in my last 20 minutes, that's just a joke. I learned this from Tony, just like in my last 20 minutes. Okay. All right. All right, so yeah, basically that was already the main point of the talk. So I sort of described a little bit what string structures are and described these two equivalent formulations, trivializations of a 2-gerb or principal 2 bundles with adjusted connections for this string group, which can be constructed in this way. Okay, so that's a long way. So now in the final few minutes, I want to explain about further going on and constructing the analog of the Spinor bundle in ordinary gauge theory, now in this higher gauge theory. And Stolz and Teichner had this fabulous name for it, calling it the Stringor bundle by analogy. Okay, Stringor bundle. Okay, so that's going to be a 2-vector bundle associated to a string structure in that sense, in the principal 2 bundle sense. So the story is, so again, there is general theory. So principal gamma 2 bundles. So if I have a principal gamma 2 bundle and a representation on a 2-vector space, and the 2-vector space, that's going to be, in the way I'm thinking about them, an algebra, right? There is this like long discussion, or what is a 2-vector space? What's a good way of categorifying vector spaces? And I think a good way is to say a two-vector space is an algebra. That doesn't sound very exciting, but the point is that the morphisms drastically change. And the morphisms between two-vector spaces are not algebra homomorphisms. They are bimodules. That makes the thing one categorical level higher. Okay, so I'm considering the Morita category of algebras on an algebra A. And so we have a principal bundle, we have a representation, and just in ordinary differential geometry, there is an associated two-vector bundle. And that's how we define string-Gauss bundle, by taking a principal string bundle, namely this here, which comes from G, which is the string structure. And now I have to explain what representation we use, and then we get the associated two-vector bundle. But let me sketch how this associated bundle construction works. So recall, picture over there, that the principal two bundle looks like this. And so what's the representation? The representation is a morphism of crossed modules from gamma, from the given crossed module, so string in our case, to the automorphism two group, to the automorphism cross module of the algebra. So exactly this thing here, so we're using now. So that's a cross module. And what does it mean? It means that, so we have H going to G. It just means a diagram in the obvious way. So H has to go to the units, G has to go to the automorphisms, and the diagram has to commute, and the actions have to be respected. So that's a representation. So if I have such a thing, and the two bundle in that sense here, then, so we have a principal H bundle and this anchor map to G. So what we get from this on the double intersections, also, let me complete it. On the double intersections, so we have a principal H bundle. We have a group homomorphism from H to A cross. So we get it by pushing a principal A cross bundle. So P, G, H, A cross. Okay. And so this A cross, so this bundle has still like this anchor map. And I extend it using the other homomorphism from the representation. So there is an automorphism phi. And just as I explained to you that like this automorphism can be used to define a left principal H, a left H action. So now this bundle becomes a bundle of bimodules for A, where one action is kind of canonical and the other action is used sort of twisted by applying this homomorphism. So the full picture of the two-vector bundle would be like this. So here is a trivial algebra bundle with fiber A. And here is a bimodule bundle, an AA bimodule bundle, and there is some compatibility on the higher things. Okay, that's how the two-vector bundle looks like that we get from this associated bundle construction. Maybe there's just time to briefly tell you what this representation is. So this representation, this is work with Matthias Ludewig, my PhD student Peter Christel, that we have carried out. And maybe the most important point is to say what the algebra is. That is, now it gets very, very strange and difficult, because an ordinary finite dimensional algebra will not suffice, right? Because, for example, we see here G is already a group of paths. This is what G is. It's an infinite dimensional group. It's not going to have any non-trivial representations on a finite dimensional algebra. That tells us the algebra must be really complicated, and indeed it is complicated. So, so this is based on ideas of Stolz and Teichner also, who say that has something to do with this Hilbert space of spinors on the circle, fermions on the circle. That's what called. So here's like a dimension of the base manifold. That's a Hilbert space. And well, there is a subspace consisting of spinors only. I should remove the, so this is just circle. So only based on like 1/2 of the circle. There is a reason to do that. And then there is also a Lagrangian subspace, so it's making some contact to Mohammed's talk, although it's not a manifold, it's just one vector space and one Lagrangian in the space. We're not doing families here at this point. And so if now there is this like usual theory, if you have a Lagrangian in the space, you get a Fock space from this Fock space, FL, and the Fock space is a module for the Clifford algebra of the Hilbert space we took. So that's what physicists always do when it comes to fermionic quantization. And so there is a subalgebra, the Clifford algebra of the subspace, and the algebra A that is relevant for the Stringer representation is the von Neumann completion of this algebra in B of F. So CLH0 double prime in B of FL. So that von Neumann's algebras appear as sort of inconvenient. I didn't ask for it, but it's also not that surprising, because when you think about like conformal field theory or algebraic quantum field theory, you have nets of von Neumann algebras. That's all related to like circles, which are around all around here. So it's not that surprising. And it was also anticipated by Stolz and Teichner a long time ago. So why is this half loop space here needed? Because if you'd just take H and von Neumann complete, that would just give B of FL. So it gives a sort of trivial von Neumann algebra, right? B of a Hilbert space as a type 1 factor. It's sort of uninteresting to say, but by making half of it, this gets slightly smaller. So it's not, the von Neumann completion is not B of H, but it's this hyperfinite type 3/1 factor. That's also a von Neumann algebra that appears often in this context. All right. So yeah, for constructing the representation, I have to cut this, unfortunately. What I wanted to say in the end, can I have a couple of minutes? Okay.
I'm biased, sorry.
So I just wanted to make this one point. Okay, so we get this associated two-vector bundle. It looks like this, okay? A is now this von Neumann algebra. And so there is a way that it is possible in this context that one can achieve that this covering thing, Y. So that comes from the string structure, right? So the two bundle I start with, that's the string structure. One can achieve that the covering space is always the space of paths based at some point in the base manifold. But like the covering map is the endpoint evaluation of the path. So paths all start at X, but like go through the space, and that is a covering space, even in the sense of it's a surjective submersion. It's a nice covering space. And one can achieve that that's the case. And let's observe what happens to the double fiber product. The double fiber product means you have two paths, both starting at X and ending at the same point. That's the fiber product condition. So the double fiber product is, up to some issues, sweep under the carpet, a loop space of, say, based X. And that means that this bundle here, this bimodule bundle, is a bundle on the loop space. Okay? So loop space. So there is this bundle S of A bimodules on the loop space. That's what Stolz-Teichner called the Stringor bundle on the loop space. But now we get, in this picture here, it is just one part of the whole part of the two-vector bundle. And another part is the coherence stuff you get on the triple fiber product. Now, finally, I will talk about the ones. So how does it look like? So we take this Stringor bundle and look at it over a loop that is composed of two paths starting at x, both ending at the same point. That's my notation for forming a loop. Two paths, and there is so this bundle also has a fiber over a loop of this form. So looking at a picture like this, 3 loops, gamma 1, gamma 2, gamma 3. So here's a loop, that's this. Here's a loop, that's this. And there is a loop that goes all around here, like this. And this coherence condition that the 2-vector bundle sort of automatically has, because it's a 2-vector bundle, means in this Eumann context that you do the confusion of these two bimodule bundles over the algebra in the middle, get an isomorphism here. That's a structure that was like anticipated by Stolz and Teichner 20 years ago. So they said there should be such a structure. And by this work here with Matthias and Peter, we finally provided it just as one of the ingredients of the 2-vector bundle. And this is important in 2 aspects that I wanted to say. So first of all, you have heard about the Dirac operator on the loop space, and it's like the holy grail of the whole field. Construct the Dirac operator on loop space and calculate its index, and the like speculation where the index lives and so on. But it's just ideas. Nothing is really known about it. And so we hope that by now finally give a neat construction of this bundle, we at least can say what the spinors are on the loop space. Not even that was clear, right? The spinors will be sections in this bundle now. It's a huge von Neumann algebra bundle. Okay, so that's one hope. That tells us, or it makes a tiny step in the construction of this Dirac operator. Other thing that's also still an open problem is to define the supersymmetric sigma model, of which I'm talking all the time, as a fully extended field theory. Fully extended in this, also in the sense of Stolz-Teichner, so many a lot of Stolz-Teichner stuff here going on. So, and the conjecture, it is certainly true, is that this Stringor bundle will be the value of this field theory on the point. That's always the difficult thing, to extend things down to all codimensions. And on the point, it's going to be the Stringor bundle. And this fusion thing here, this operation, that provides like one important information. So if you extend field theories to a point, you are able to cut off circles, right? In this sort of, if you think about the Touraev-Reshetykhin picture of a TQFT, that's only extended to dimension 1. So the basic thing is a circle and everything else is built on circles. But now if we extend to a point, we want to cut circles. And if we want to cut circles, we need an operation like this. It's like the compatibility with the composition of one morphisms that you don't see unless the theory is fully extended to the point. Thank you very much for your attention.